What's up YouTube? This is Matt Brown with another IoT hacking video. Today we are taking another look at the Mercusys 4G LTE router, and last time we got UART on this device, but it was a very limited UART console. We couldn't get a shell, we couldn't even get into the bootloader, so we are going to have to go ahead and perform a chip-off firmware extraction on this device. So that's what we have in store for our video today. Before we jump into it, please subscribe if you enjoy this content. It really helps out me and the channel. Let's head over to the desk. So here I have the device. I got the PCB already taken out. Power cord's all disconnected because everything we're going to do today is going to be we're not with the device itself powered up. So we are going to be targeting that flash chip like we talked about in the last video. That is very annoyingly hiding underneath this shield. Let's take a really fast look at that under the microscope. There you can see that we really only have 2 of the 8 pins exposed here. So we are going to have to go ahead and remove part of this shielding to even get access to be able to perform our chip off on this device. And so what we're going to do is we're going to kind of do a combination of, I'm going to throw some heat at this device, and then I'm also going to try to just pry it off. Sometimes you can just kind of, I can just kind of use my, some tweezers, some clips, some snips or whatever to get this thing off. And so we're going to try all of those approaches at once. So the first thing I'm going to do is I'm going to use some of this heat resistant tape. And if I can find where the tape starts, you know what? I'm just going to use this stuff I have right here. And the main thing that I'm wanting to cover up, if I can get this to work correctly, is so the plastic on this little connector that we soldered onto the UART pins, that will melt if I put too much heat on that. So I'm just going to kind of just cover that up like that. I really don't care about this material here, but it would be nice to shield that with my large tape, and yeah, I just can't find. That's hilarious. You know what, we're just going to use a little bit of this just to shield the edge that's closest to our target. Gosh, I can't do that within these gloves, can I? All right. Yeah, that's garbage. Here we go. Yeah, really we don't care about that. We're not going to be throwing heat too far over there. We're going to be throwing the heat right here. And again, I'm going to be trying to like snip off the shield as well as throw some heat at it. So we're going to do that all under the microscope though. So here we go. Firing up my air extraction so I'm not breathing in all this crap. And then I'm going to start throwing some hot air in this direction. Because, actually before I even do that, let's just go with the physical pry method. So what we're going to do, so we're going to, this is so precarious because there's all these little components, and I definitely don't want to screw up any of those components. But usually, what I can do with this, there's not as many components directly on the outside. So what I can do is I can kind of pry outward. Yeah, and get it to come off. Oh yeah, there we go. Okay, sweet. I don't think we need heat for this. Oh yes, perfect. Now we're just gonna. There we go. Nice. Okay. I'll just bend this back and forth a couple times. It'll break off. There we go. Perfect. Well, that was easy. Okay, and we can even like bend this back a little bit. That's what I always notice about these shields is that you can usually just kind of like break them off of their edge if you don't need them to stay on, which I never do. Yeah, you can just do that. Oh. Whoops. Well, this system's dead. All right. I probably just destroyed everything there. Let me see. Okay, so this. Where did this one come from? Oh my gosh. All right. Well, that's fun. So that's the downside of doing it that way. All right, let's get some heat. And let's get my tweezers. And let's see if we can perform some surgery here. Whoop. Well, that was excellent. All right, so this device is probably bricked, but the flash chip, we can still finish out this video, but we're probably screwed. All right, so what we're gonna do is we are gonna lift this chip off. We're gonna continue with the firmware extraction, and yeah, definitely screwed up a bunch of those components. We'll see if that matters. We'll find out. Sometimes it doesn't. Oh, wait. Actually, I wanna figure out right now if it matters. I want to figure out right now if it matters. Okay. So really quickly, what we're going to do is we're going to power on this device, and we're going to connect up to UART, and we're going to see if I completely bricked it, or if that stuff didn't matter for some unknown reason. Okay. So now what we're doing is we are connecting to UART, and okay, this is not planned. So what we're gonna do is we're gonna go back over here. We're gonna spin this up so you can see. Make this nice and big. Pico com. Okay, there we go. And the moment of truth. Whoa! Woo! We didn't brick it by knocking tons of components off the board. You never know. You never know, folks. All right. Anyway, we will resume our plan here of, well, one, the plan is to not knock any more components off the board. That would be super ideal. You know, there's just a cap missing. No big deal. Okay, but we are, okay, so back to the chip off. I love these little flash chips. They don't take nearly as much heat as those big, you know, 48-pin chips. It's just like, bam, just like that. It's done. All right. Setting the board to the side. Okay. We will try to clean this up a little bit. Be professional, as you can see from the video so far. That's what we do on this channel. We keep it very professional. All right. So, I got some wick, my soldering iron. There we go. We're cleaning that side. Cleaning this side. Trying not to burn my fingers. Partial success. All right, there we go. All right. That is good enough. All right. Now, what we're going to do is I'm going to find my adapter right there. Let's refocus. Hopefully this is the right one. Oh, it is. Nice. Okay. And again, I just know that on the XGeku, the universal programmer I use to read these chips, it always wants it down towards the bottom with pin 1 facing up. So there we go. That looks good. I'm like a perfectionist here. I'm a perfectionist with shaky hands. It's the worst combo. All right, there we go. Turn off my air extraction. Don't need that anymore. Okay, go back to the desk. Okay, so there we have it. Our chip is in the reader, and now we're going to bring over our reader here. So we have pin 1 is located up here. We want pin 1 on the chip to face this way, but be all the way down at the bottom. This is diagrammed in the official Xkaku software, but we are not going to be using the official software. We're going to be using the open source Linux, or just open source alternative that runs, that is a cross distro, cross OS, whatever you call it. All right. Okay, there we go. We thought the whole video series was going to be a bust, but it wasn't, because somehow, magically, the device has not been bricked. Okay, so let's go over here, and we are going to perform the firmware dump. So we're going to be using Minipro, which is the open source piece of software that I have been shilling on this channel for a while, ever since I discovered it recently. It is the open source alternative to the XG Pro software, which is the sketchy Windows software that I used to run under Wine. Sometimes I still have to run it. There's some chips that aren't supported on the open source software yet. Thank you very much to the maintainers of this software. So I've already, followed the install instructions, so we're not going to go over that again. I will put a link to this repository in the video description. Highly suggest using their software. So what we're going to do is we're going to run Minipro-L, and then the some of these identifying character, the serial number of the chip. And so we talked about this last video, but we found the data sheet for the chip in the last video, and it is the Giga device, which is like, that's kind of like not a name brand flash chip, or at least not one I see a lot. 25Q64E. That model number is like, a lot of other people have the same exact spec chip. So that is very common. So we're going to just search for that specification with the -L command, and then we get a bunch of different options. So we're going to use the SOP8. That is the package of chip that we have over here. Like, all of these are going to be the same pinout, and I'm pretty sure the same like voltage and everything, so that really doesn't matter. So then what we're going to do is we're going to say Minipro -P. We're going to paste in that specification for which chip we're trying to interact with, and then we're going to do -R for read. We want to read off of the chip, and then let's just read it into a file called firmware.bin, and it is going, which is a good thing. That's a good sign. And so there we go. And what I'm actually going to do right away is I'm going to read it a second time. This is something that has screwed me over on so many pen tests, where I'm working with a firmware, I'm like beating my head against a wall because I can't extract a file system, and it turns out I just had a bad read. Something wasn't seated right in the programmer. So as a sanity check, I always like to do this, where I will run MD5sum and I'll dump the chip multiple times. It looks like there's some like EEPROM data also. That's actually super interesting. And it's all blank. Oops. Yeah, that's all blank. Okay. We don't really care about that. What we really care about is the fact that our test succeeded. So firmware and firmware 2 have the same hash, which means that we can be pretty confident that we had a successful read of this firmware. It is, let's look at this. We can see that it's 8 meg, so pretty standard size of chip for this package of chip. It's not a lot of storage, and so it's a pretty small, lightweight embedded Linux system that we're dealing with here. So now what we're going to do is we're going to run binwalk. And I have binwalk and binwalk v3 installed on my computer, doing some dev and test. So I actually have Binwalk v3 symlinked to the version 3, the new version of Binwalk that's rewritten in Rust. It's very fast, very awesome. Highly suggest you use it. So what we're going to do is we're going to run that on, actually what we can do is we can rm everything like that, and then we're also going to get rid of this EEPROM thing because we really don't care about that. We're just going to run binwalk v3 on that file, and okay, so one thing that I don't like about the new version of binwalk is that I can't make the text really large, otherwise it goes away. All right, so here we go. We have a couple of file systems. Okay, this is awesome. I'm really liking this, that we have some, okay, we have one squashfs file system. Okay, that's probably the root file system, but then we have a couple of JFFS2 file systems, which are writable, right? So we could potentially change those on the fly from a UART shell or something like that, but this is awesome. Now we're going to run the -e flag to actually allow Binwalk to perform extractions on this firmware, and we're going to just do a little bit of very quick analysis, show you my first impressions. This is the first time I've ever looked at this file system, obviously, because I just now ripped the shield off of that device. So, all right, let's see what's in our extraction folder. Okay, what I'm really interested in is the squashfs file system. Let's start there. So it's in this folder. Oops, don't need CD twice. All right, so we have a squashfs root directory. We have all of this stuff. Let's just run tree here. Okay, we have XML, interesting. Okay, so we have like a main folder with a bunch of HTML files. Cool, so this looks like a web server of some kind that we would be serving up all this content. Yep, okay, it's in the web directory. That's really cool. Okay, so what I want to start with, okay, so if you remember from the last video, in the UART console, we saw a bunch of stuff about like SSH, about SSH keys being generated. Well, Dropbear, that is a lightweight SSH server that exists on a lot of embedded devices. That could be really promising. So we're going to want to look into that eventually as a part of some security analysis that we'll do. Okay, so password. Ooh, if there's like a password.back file. Okay, let's go. Oops. Oh gosh. All right, hang on, everybody. Don't want to dox myself here. Mercusys. Let's go back to where we came. And I want to go into the Etsy directory here because, okay, there's an interesting symlink that it symlinks password to var password. It's like, okay. So var password would potentially be in one of those other file systems, or it would more likely be a temporary file system. So that's not telling us a whole lot, but what is password.back? Because that's super interesting. Okay. This is fascinating because there is a specific Dropbear user, right? I mentioned this in the last video. One of my like things that my like my spidey senses went off when I saw stuff scrolling in the UART. It's like, what if the manufacturer has like a backdoor or a way to like not really even a backdoor, just like a way to SSH into the devices and have persistence on all these devices in the field. If they're doing that via SSH, that would be really interesting. I'm sure customers would probably like to know if the manufacturers had that capability. But here we have this password.back file. We have a password hash, which is really cool. Okay, so the first rule of trying to crack a password hash before you put it in your super big password cracking rig is you Google for it. All right, cool. What do we got here? Let's search for it. The passwords are stored in the old way. I'm reading this for the first time, everybody. Okay, admin at 123 is the root password of the router. Awesome. Okay. So now that's in that back file, so that might not actually be active, but if it is, that's crazy. Oh, this is like, okay, this is crazy because this is, okay. I also mentioned in the last video that Mercusys is a company that is owned by TP-Link. It's one of their like, you know, other brands that they sell. I think they market it in like not North American regions, right? So it's like APAC, other regions of the world is where this really gets targeted. Okay, but they have something about drop bear. This is what's really fascinating. Another interesting user here is drop bear. Da 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 da. Okay, so they did some analysis. Definitely going to read this. This analysis here that somebody else did on obviously a similar device. But what we got here is that they say that this hash, they cracked it as 1234 is the root password. There's the admin password. So we're gonna put the chip back on the device and we're gonna see if that is actually the password here. Okay, I don't see anything else. Okay, what I want to do before we jump back and put the chip back on the device is I want to look at those other file systems for a second. And I just want to see, okay, there's some decompressed. Okay, find, what, anything in there? What? Okay, no, nothing in there. What about these other file systems? Okay, that's interesting that those were not really able to like get anywhere. Oh, here we go. Okay, there's something interesting in there. SMS DB. Oh, that's cool. Oh yeah, that's a SQLite database. Let's see what's in here. Select everything from SMS. Nothing. Okay. Select everything from raw. Okay, it's the world's most boring SQLite database that we've ever found. Definitely a much more firmer analysis that we would do in an assessment or reverse engineering engagement. But let's put the chip back on the device and see if we've figured out the hard-coded password for the root user. I'm kind of hopeful. that will work. Okay, so back to the desk. Here we go. Let's get my tweezers and get this chip back into action. Don't need the universal programmer anymore. All right, let's set that down. And back over with the microscope. Here we go. All right, so pin 1 indicator, that circle right there. Hang on, let me just like unplug, because we do not need this plugged in right now. Let's just get this super focused there. And then let's get this set up. So what we're gonna do is we're gonna take a little bit of flux. And we're gonna put that right here. Oh, that's like almost too much. There we go. And we're gonna turn on my air extraction. And now we're just gonna clean up this old solder. So the way I'm gonna do that is I'm gonna start by dropping just a little bit of new solder on here. You know, that actually looks pretty good. We're just gonna roll with it. No need to take the solder off and put it all fresh. If it was one of those 48 pin chips, I would definitely do that because those are a little more finicky. But a little bit of flux, some heat and some solder, this is gonna go right back on. Oh, here we go. Come on, man. All right. That is not the best job there, but I think it will be sufficient. So I'm going to carefully put this back here. Just like that. And we're going to pop over here to our UART interface. Okay, I was like, oh, again, plugging in the power cord, kind of important. There we go. Don't need my air extraction on anymore. All right, here we go. Okay, we're gonna let it boot up completely because, here we go. Okay, admin, whoa, there's a lot of stuff going on here. Okay, typed admin, 1, 2, 3, 4, and we're in. We did it. Awesome. Always Google your password hashes or DuckDuckGo or whatever. Search it on the internet because that is the guaranteed fastest way to crack the password hash if it's, you know, searchable on the internet. Awesome. All right, so what the heck? All right. Hello. Here we go. What do we got here? This is fun. Very cool. All right, so now we have rooted our device just by performing firmware analysis. We didn't even have to do modification of the firmware, which is really cool. Like in theory, if this device, it's not, if it was running secure boot, right, then this would have gotten us the shell, whereas firmware modification would fail, assuming the secure boot was implemented properly. But here, by, you know, figuring out what the password hash was, the hard-coded password hash, which is hard-coded on every device, obviously. And the way we know that is because we found it in the squashfs file system, right? So the place that we found it was in 1500. That was in a squashfs root file system. And that file system type is read-only by its nature. It is like you cannot write to a squashfs file system. You can't. That's what those other JFFS2 file systems are for. So now we have control of the device. I need to get a SIM card for this device now so we can start to play with it and actually allow it to connect to the internet, because it's obviously doing a bunch of really interesting phone home, like it's kind of, you know, trying to phone home, right? It's creating the, it's gonna, you know, go to this. It's going to go to this server out there. So I'm going to get a SIM card. We are going to play with this thing and see what we can find. So thank you for watching this video as I stumble around and almost brick a device. But that's how it goes sometimes with this stuff. And you just have to keep rolling and try to solve the problems as they come up. Thank you for watching this video. Please subscribe and comment down below. Tell me what you want to see in the future, what kind of content, what you like, what you don't like. I really appreciate everybody's comments. Have a good day.